Hello, good afternoon. My name is Patricia Wong. My team members are Eric Camacho and James Carvalho, and our senior design project was to make a force converting stage for a Nanoindenter. These are the key points that we're going to go through during our presentation. Problem statement, motivation and goals, prototype design, environmental issues, economic aspects, global awareness, and lifelong learning. A Nanoindenter is a device that does material testing. It applies one single compressive force onto a material, and it tests nanomaterials such as nanowires and biomaterials like collagen. The problem statement of our senior design was to make an insert to convert one single compressive force into tensile force. So to make a push into a pull on the material. The motivation of our project was to increase capabilities of material testing. What this Nanoindenter the testing that it usually does, the compressive testing, you're limited to those mechanical properties, and by doing these tensile testing, we brought in the mechanical properties that you take from the material. And also explore the capabilities of the 3D printing, because we're printing in such a small scale that we really had to design to be able to 3D print in a certain 3D print. The literature survey that we used was a publication and a patent done by Rice University, and this is the stage that they made on a wafer, which they applied a single compressive force in the center on the top center, and then the material they placed on the midsection on the bottom. And the conclusion that they came to was this relationship between the tensile and compressive force. The standards that we applied during our project were the Coop and Vickers hardness of materials, standard practice for indentation testing, and standard guide for printing inks. This is the evolution of our design. We originally started with the Rice University design as our basis, changing the angles. And after we came up with the Delta design, and we took off the whole bottom of the insert, and then so they would be able to stand on their own, we added supports. Simultaneously, we took the simple concept of a sphere, and we went through a hex flex and a flex 360 design.
So our final design is a Flex 360, which is named after the fact that it's made out of Ninja Flex, a 3D printing filament. It's very flexible. Going over our design iterations, we started with the original Rice design, and this brought us an introduction into the problem, what kind of things had to be faced. We noticed that there were problems with the fact that we wouldn't have this elongation along the testing side of the material, as well as stress concentrations around where those columns would meet. We elongated those columns, in order to have that higher displacement. But now that when we did that, we had to deal with buckling, and now that the columns were longer. And so we decided we were thinking about a design that would distribute this load and wouldn't sort of jeopardize the structure. And that's how we came up with the spherical design. But the immediate problem that we face with this one would be you wouldn't be able to look at that displacement along the testing side for the material. And so we had the Flex 360, the Hex Flex design, named after the fact that it has hexagonal units along a ring structure. And the same with this, the structure was complicated, and any small deformation or any small imperfection during the 3D printing process would cause the alignments on the loads along the structure and we also had stress concentrations along where the structures connect. And so we smoothed it out into our Flex 360. It's a simple design that uses sort of a compressed ring, so the outer edges are stretched, and it's a sort of universal concept that everybody can understand, and it's part of our global perspective into this design. It can be scaled easily, as well it distributes the load throughout its design and transmits the load into the testing site.
So once we had our final design, a lot of different analysis we've done, trying to create the best shape we can get. A lot of the things we've done were design studies done measuring designing the highlights from the device, the platform thickness, the actual thickness of the platform, the ring thickness, and the thickness in the Z direction of the device. Here we see is stress analysis of the actual stage of Flex 360. As you can see throughout the most of the device stays safe in the blue areas using the here on the right hand side, using noticing stresses where the most stresses, the major stresses that we see occurring are exactly at the top where the force is being applied, and also where the actual device will be fixed with the Nanoindenter using multiple different supporting techniques. The max stress you can, as shown is 0.19 gigapascals, which is being seen or foreseen developed here in the top area where the force is being applied. But throughout the device, it stays neutral. So the main goal of this device was to have a compressive force go on top and create a tensile force here to create a displacement where we can attach a material, nano wire or whatever material being tested at that point in time into the middle. And so to actually get from these dimensions the actual distance and force, we embedded sensors into the faces of each individual platform, testing platform. And the first figure we get was the original distance between them, we placed them, is 0.05 millimeters. Now knowing that, we ran the simulation, and we can see here that the figures are more deformed. The force is the greater distance increase here. The force that we got the elevation that we have was 3.43 millimeters between both platforms moving in opposite directions, and which in turn turned into a 680 degrees on maximum strain on actual material that would be placed, that would experience if the material is placed right here in the middle of the platform. So once knowing that and the way we were able to get the actual forces in out of the actual the forces that actually get what the materials are expressing is we use a material that we know the known E, the known elastic modulus, the constant area, and original length, and we would use a correlation with these type of equations where we can correlate a compressive force and a tensile force, and knowing the factors that we know of this material knowing in the middle, we would get a tensile force. Now moving on to more of the construction of our actual devices and prototypes. Originally we started with using PLA, but due to certain physical conditions, and you've seen that PLA is not as flexible and won't distribute our forces as good, we move on to rigid flex, or way more flexible material, and will give the elastic properties that we're looking for. Which also we use also as well MakerBot replicated 2D printer, 2X printer for our applications. The printing capabilities were decent enough to reach a certain point in our design process. And approximately the build time for each design shown, except for the spherical design, which we never got able to properly set up the print, was approximately 15 times. So this is include actually prepping the design in the actual software of the MakerBot, and dismounting and mounting materials onto the printer itself. Okay, so we were going to use the simulations that we got from SolidWorks and test them all, compare them to the results we got from the Nanoindenter testing. Now, due to certain issues, we had to scale up our design and use a microindenter test, which is this shown here, a device being placed in a microindenter, to simulate how it would actually operate inside an indenter. So here's a video showing the actual the scaled up version of the 360 design that we're using. You see the force being applied from the microindenter, and seeing the movement along the ruler here we have shown. That's a little bit hard to see because the contrast is both things are white, so the contrast is a little bit hard to see. Now here we have this is the correlation that they have between the RISE team got between their device, their MEP device, and this is the correlation we have from ours. Using the simulation that we mentioned earlier, we simulated a nanowire being placed in SolidWorks, being placed in the middle of the platform, and throughout the different techniques, we were able to get that the forces that are being applied on top is 0.13, times 0.13 equals the forces that are being developed tensile and the acceleration in the testing platform.
Reflecting onto our year-long experience, we realized that the biggest gain we had was our 3D printing experience, as it's a technology that's becoming more popular in industry, and it led us to experience that process as between students and professional engineers as going towards what's conceptual and in design, and to what can actually be done. Such experience we summarize with the quote, "Design is a plan for arranging elements in such a way as best to accomplish a particular purpose." So we had a certain amount of materials available, and we designed our insert to meet that purpose. We considered the environmental impact through the design of this project, considering the fact that we do not need heavy machinery or machinery that requires heavy input. As it was previously mentioned, printing takes 15 minutes, as well as the final printing result is about an inch in height, so it's not very much material, and it can be recycled. In terms of economic impact, this is a testing project that develops testing capabilities for a Nanoindentor, and so it's a beginning step into developing that capability and to further develop the technology that's driving multiple industries. As well as it didn't escape our thought the fact that this was a project that was started by Rice University and is now in FIU and will likely be moving around in multiple universities around the United States as well as the world. And so this is a sort of global project as engineers try to pursue better technology.
This project, it allowed us to collaborate with our peers like we would do in industry, and also it helped us see the importance of time management and the use of standards when doing a project like this. This was a year-long project. It started in August and it ended now in April. And our design is a easy to manufacture design. It's a simple concept that is well known and it's inexpensive. And for future work, we would want to adjust this fixture so it has we can use it make it in different dimensions for each material that we're actually testing, and scale it down. Try to manufacture it in a different way, maybe using a different 3D printer that prints in a different scales. Also taking into consideration, because we designed it to be a multiple use indenter, maybe just have it for one-time use. And then for the material testing, we would place it onto our fixture by using epoxy, or if we use metal, we can do a micro welding onto the material. And we would like to give special thanks to our advisor for his expertise in this endeavor, and to the other people that helped us in our process. And this is the end of our presentation. We would like to open the floor for questions.
So I've got a question. If you go back to the slide real quick that showed your force equations versus the Rice force equations that came as your results. One back there. Is the goal to get as close as possible to the compression force, or as far as possible from the compression? I mean, are you targeting a specific force, or are you targeting the closest possible to the controlled force?
Well, we're trying to get the maximum force we can develop from that site. We're not really trying to reach the compressive force, but we're trying to develop the max force that we can. If we can close to the compressive force, then awesome. But you're trying to get as much force as possible.
We wanted to get a known relationship between the compressive and
And then that would depend then on the instrument it's being tested on, because obviously if your instrument can create a more compressive force, it would be more beneficial to you that way.
Yeah.
Okay. Anything else?
Did you, when you're looking at the simulations on your FEA analysis, did you go back and do hand calculations to see if you did a hand if your numbers were right, what you were expecting to find, or did you do anything like that?
No, to get the forces.
Right, in other words, did you do your own calculations on the side and say this is what we should be getting, then when you look at the simulation, were they comparable, or did you even do that?
No, we did not do that. We were going to compare our simulation results to our estimate from testing, but we didn't get to actually test in the macro, in Nanoindenter microdosing. But we did not do those hand calculations. No, we did not.
Okay. I'm just curious.
So to follow up on that really quick, I'll have a couple. So you did put it in the microindenter, right? So you did apply a load there. Did you guys do that simulation?
Yeah.
Yeah.
That specific load that you had in the microindenter, you did that exact simulation?
The actual load that we put in there.
Yeah, so what is the load that you're applying in the microindenter?
Well, we simulated it. We're applying the same 10 gram force, which they use 10 gram forces as the setting. So we applied it for a 10 gram force, and then moved. I can't remember the actual number, but moved a certain distance.
So you applied a force, it measured a distance. You didn't think to compare those two at all? To a simulation that you ran?
Yeah. The forces being applied on Nanoindenter, we had to increase the forces, so to get movement.
Hang on. You applied a force with the microindenter, correct? You had some displacement. We saw the video on the previous slide, right? Did you run a simulation on that exact experiment and compare your results with that result?
No, not with that.
Right. So just going, can you go back to your simulation really quick?
Which one?
The very first one where you showed, yeah, that's perfect, right? So what's the yield stress of your material?
The yield stress?
Mm-hmm.
The actual figures I can't remember at the top of my head right now.
All right, it's around 40 megapascal, and the simulation is 190 megapascal.
The things, these numbers that we got for our material properties, were we got from a chart from actual NinjaFlex, so the numbers are different.
Okay, right. So what is the actual yield stress of the material?
I can't remember the point out.
Is it you're saying it's higher than 190 megapascal?
No.
We have it on a chart.
I think it's
So 190 is typically the yield stress of steel. So I don't think that NinjaFlex has the same value, right? So essentially the simulation that you have here, which is the foundation of your project, right? I don't know how we can trust this original simulation going forward. Have you guys thought about that?
well, 190 gigapascals is the max stress.
Megapascal.
190 megapascals is the experienced stress.
Correct.
The yield strength was actually 20 gigapascal,
20 gigapascal?
according to the information.
There's, so the yield strength or the ultimate strength of diamond is 3 gigapascal, right? So you put yield strength is 20 gigapascal in this simulation?
20.564.
Yeah, again, right, so. Did you guys try putting any weight on the top at all and trying to see how it corresponds to the load or the force of the displacement?
Are you talking about actual prototype load? I used a prototype actually to put a load on
Yeah,
top.
some
Yeah,
numbers.
we
right?
put different loads, different weights, but using a 1 gram force that 1 gram that Nanoindenter would produce it, there was no movement. And we tried out 2 grams, there was movement as well. So we didn't get actual recorded movement from those.
Okay, so you put that same load here and you got forces that are well exceeding the typical yield stress, right? You're saying here the stress analysis is 0.1 Newton, correct?
0.01, yeah.
0.01. So you're saying that applied load here creates 20 times the yield strength of the material, and yet you saw no displacement when you put on 1 gram material.
Yeah, the one we put weight on was a scaled up version, so this would be different. This was a.
So did you ever try validating your simulation against something in the real world?
No, we did not get to validate this simulation because this simulation required, the dimensions of this actual 360 was what we were predict.
All right, that's my main question.
But you didn't go back and, because you said you have a scaled up version of what
Right.
you tested. Did you go back and run a simulation?
We ran simulations, but
The measurements?
the numbers that they were producing were so small that there was, you can consider, say, movement in that direction, so small that would be
But
I
you
guess it
showed,
was
you
a-
showed a video where it moved, right? You showed a video of significant movement, right?
But this simulation was done with a scaled down version of what we actually have.
Again, well, what I'm saying to you, anyway, it's fine, but what I'm saying to you is the numbers that are coming out directly from here are completely infeasible numbers, right? So do you trust this simulation?
Well, at this point in time, seeing those factors, we cannot say that we trust the simulation.
Okay. So then what other foundation for the project do you have that goes into actually designing a structure, right? So the main output of this thing was you want to try to correlate vertical force with compressive force, right? Or compressive force with tensile force, right? So if you're saying this simulation, out of this simulation you got a value of 0.13, but you don't trust this simulation, what is the main metric that you are using in your design?